Hello and welcome back to the second part of this talk about integrated multi-trophic aquaculture as part of the Integrate project. In the first part we discussed a little bit about what the global position was for food production, why aquaculture was an important component of that global food security, and what are some of the problems facing aquaculture. In this second talk I really want to talk about how IMTA, Integrated Multi-Trophic Aquaculture, can help deal with some of those environmental issues. But first of all, we really need to understand what we mean by Integrated Multi-Trophic Aquaculture. It's not a particularly easy and identifiable acronym, but what does it really mean? Well, part of the problem with the development of IMTA within Europe is that there's no real definition. There's multiple definitions for a lot of different systems. So what we're going to do today is talk a little bit about a generic fin fish production system that might be applicable to sea bass or sea bream in the Mediterranean or Atlantic salmon in the Atlantic. So the concept of integrated multi-trophic aquaculture, the clue really is in the word integrated. It's growing different species at the same location. So a lot of European aquaculture at the moment is monoculture. So at one site you'd only grow perhaps Atlantic salmon or sea bream. You wouldn't grow other species alongside that. But the idea of polyculture is actually quite old. So polyculture means where you grow lots of species together, and around the sort of 5th century in China, they were writing treatises and texts about the polyculture of carp in ponds. So the idea is quite old, and there's several advantages from the concept of polyculture and for IMTA, where you use the waste products from one species as the nutrients for another species. And that normally happens within an IMTA system at different trophic levels. And when we talk about trophic levels, all we mean is the difference between herbivores and carnivores, or herbivores and primary producers. And primary producers are things like microalgae or seaweed. So if you remember, we showed this diagram in the first part of the talk, where we talked about the issues about aquaculture, it being a linear economy with raw products going in and waste products coming out the bottom, and our main product, which we're interested in fish, being the only product we create. The idea of IMTA is really to create a circular economy for the aquaculture industry, is to allow some nutrient recycling of those waste products, which at the moment are lost to the environment, but can be captured. Now, there's two things we need to think about when we talk about the capturing those nutrients. First of all, there's obviously an environmental benefit from being able to reduce the amount of nutrients in the environment, but there's also an economic benefit. The input of fish feed normally represents around 60% of the total cost of any aquaculture operation. So it's a really expensive component of the industry. And a lot of the value in that comes from the protein that's included, which as we discussed, comes from the capture fisheries. A lot of that protein is lost and wasted as nitrogen that comes out of the bottom of the cages. So if we can use IMTA to recycle that really valuable nitrogen into other products that the farmer can use and sell, then not only do we reduce the environmental impact, we can also increase the profitability of the business. So as I discussed earlier, the waste from fin fish aquaculture can be broken into sort of 3 elemental groups: nitrogen, phosphorus and carbon. These first 2 groups are normally released as dissolved waste, which is dissolved in the water column. Normally fish waste products, but also leaching from the feed. So, and because they are dissolved and in inorganic form, they can be rapidly uptaken either by seaweeds or by microalgae. But when you're in an open water system, it's normally seaweeds which you're employing to mop up those dissolved nutrients. The other component of fish feed, as I discussed, is really solid waste, either in the form of uneaten fish feed or in the form of fish feces. And two things happen to those solid wastes. The smaller bits will float on the current and be dispersed in a plume away from the cage. The heavier particles will sink relatively rapidly to the seabed. So out of that solid waste stream, you've got two different types. You've got those which float and distribute, and those which sink rapidly. And because of that, you need two different types of organisms to deal with them. So to deal with the lighter floating particles, in an IMTA system, you may want to culture shellfish that filter feed and can filter those particles out of the water. And this is traditionally bivalve mollusks, things such as mussels, scallops, or oysters. And they all have a huge capacity to filter the seawater, take the particles that they want, which includes the waste from the fish farm, and convert that into flesh. And so you create a valuable product in either mussels or in oysters. For the heavier components, which sink rapidly to benthos, really you're not going to have enough time to intercept them in the water column. So what you're trying to do is have an organism that can live on the benthic environment. And when I say benthic, all I mean is a seabed. So an organism that happily lives on the seabed who can make use of all that extra food which is falling down out of the water column. And that's traditionally echinoderms, so things like sea urchins or sea cucumbers, or it may be things like annelid worms, which can live in the sediment and make use of the feed that falls from above. But in this way, we create not only the fish product, but we also create valuable products in terms of seaweed and filter feeding, things like mussels and oysters. And as these organisms grow, they take in the nutrients and remove them from the water column. So these we tend to term are extractive organisms because they are extracting the nutrients from the water columns, but they also, in their own right, can be very valuable products. So this is a type of IMTA system we may want to develop along for an open water system along the Atlantic coastline. So when we look at IMTA, we need to understand that, as I say, polyculture has been going on for hundreds of years, and IMTA has been going on in Asia for maybe equally long periods, but certainly for maybe hundreds of years. And it is now a major component of the aquaculture systems in places like China and elsewhere in Asia. In Europe, we've been looking at the IMTA for about the last 40 years at a scientific level. We've seen the benefits and the type of systems that are happening in Asia, and we've tried to look at the scientific benefit of importing them to Europe. But despite there being quite clear evidence that IMTA can work, it can reduce the amount of nutrients in the environment, it can increase the growth rate of the organisms, the extractive organisms that you're culturing alongside the finfish. There's been relatively little uptake in Europe for IMTA, relatively little commercial uptake, that is. So part of the Integrate project is to try and understand what are the bottlenecks to industry in Europe using IMTA more regularly. And this has received a lot of interest from governments and regulators. The aquaculture industry is increasingly coming under pressure to reduce its environmental impact, and regulators and governments are looking at IMTA as one possible mechanism to allow the reduction in that impact. So the diagram I showed you just now was really what we called an open system of IMTA. It's IMTA based in the open oceans, but there's two different types of IMTA basically. There's open systems which we've discussed, which are where the fish are in sea cages, and it uses the natural hydrodynamics, the natural water movement, such as tides and currents, to move those nutrients from the finfish to the extracted organisms. And there's closed systems, which tend to be tank-based, but they can also be pond-based systems where you use artificial controls such as pumps or channels to move the water from your fish production to your extracted organisms. And there's some fundamental differences between the two types of IMTAs in terms of the control and in terms of the scale. So here we have the open water IMTA system, very similar to the ones I previously described, where you have the cage of your fish, your primary product, and in this diagram, the current, the water current, the main water current, is moving diagonally upwards. So the first set of organisms you have after the finfish to catch those lighter particles are mussels, which are filter-feeding invertebrates, which can take out the smaller particles. And after that, you have algae, which can take the dissolved waste out. So you can imagine that there's a gradient of how those different components travel, with the particulate waste traveling least distance and the dissolved waste traveling greater distances, and therefore you tend to put your seaweed further away than your shellfish. And underneath here, you would have your benthic components such as sea urchins or sea cucumbers. Here's an example of what it really looks like in reality. This is an open water system that was developed here in Scotland. And you have 12 salmon cages on one side and downstream from them. And this is, when I say downstream, it's down the tidal stream. So the tide is running up and down this sea lock. You have your IMTA system here. And it has very little above water because it's mainly dealing with species which live in the water column. So within that grid you saw just now, you have oysters growing, you had mussels growing, you had queen scallops growing, and they were growing closest to the salmon cages. And behind them you had seaweed growing, and in this example they were kelp species, so the fast-growing brown seaweeds. So your filter-feeding invertebrates here were making use of the particulate matter, while the seaweeds were making use of the dissolved component. So this is an example of how an IMTA system in Europe might look. The other type of system, which also has an important role within Europe, is a closed system. And these are onshore systems. And as I said, they could either be in tanks or in ponds. And one good example of tank-based systems tends to be hatcheries. Hatcheries for finfish tend to be onshore, so you have greater control of the life histories and the reproductive processes. So you're pumping water into tanks, you're growing the fish in the tanks, and then generally that water is just then pumped back out to sea. So again, it's quite a linear system traditionally, but it does allow us scope to implement IMTA and circularize that system. So the main differences between closed systems is that, as I said, and open systems is that you have much greater control of the inputs, but traditionally the scale of production tends to be much smaller. And you can see this is a small IMTA system set up for a hatchery in Scotland. So the hatchery was producing cod and halibut and sea bass, and the brood stock were kept in large tanks and fed a pelleted diet. The water from those tanks was then transferred by a settlement tank into the 4 raceways. And in the raceways, you had sea urchins and worms. The worms were particularly good at feeding on the dense particulate material that fell out from the feed. And there was also worms growing, in this case, in the settlement tanks. The sea urchins were also good at picking up individual particles, and the experimental evidence showed that they were capable of growing well on those waste particles. And after that, you had the growth of ulva, which is a green seaweed, which was able to make use of the nitrogen and the phosphorus, the dissolved components of the waste. So, given that there's these two different systems, there's open water and closed water, what makes a good IMTA system? And here we're going to talk mainly about open water systems. Well, the most important component to understand and defines what makes a good IMTA location is understanding what the tides and the currents are that would link your finfish production with your extracted organisms. So if you're relying on just those natural currents and tides to move the nutrients, you need to have a good understanding of what they are. You also need to understand what species you're going to grow and how they can extract the nutrients. And you've got to understand whether the species are going to grow well at your location, whether they are local to your location, and whether they are commercially viable, which is absolutely crucial because ultimately the farmer really wants to be able to increase his profitability. So, as I was mentioning, market value is a crucial component of the IMTA system. And so when we're talking about shellfish, we already know that there's a good market for oysters and for mussels and scallops. So their integration in an aquaculture system is fairly easy because the farmer knows there's a defined market. For seaweeds in Europe, this is much more difficult. So seaweeds are the important extractive component for the dissolved wastes. And while they grow really well in the Atlantic, and while IMTA can increase their productivity, what is less well understood is where those seaweeds can be sold, how they can be turned into a commercial proposition. The other thing we need to have is a system which is relatively low maintenance, because the more maintenance that a fish farmer has to put into his IMTA component, the less he has for his main crop, and the more expensive the more the additional cost of the integration is going to be. So we need to have systems and technology which allows rapid grading and cleaning to reduce the costs. We also need to have the correct storage systems and the correct harvesting systems for the integrated components. So a lot of finfish farmers have really well-developed harvesting and production systems for the finfish. They don't traditionally have harvest and production systems for the shellfish and for the seaweed. So these systems need to be developed, and there needs to be suitable capability of a finfish farmer to deal with the additional products. So in that last segment, in the second segment just now, we've talked about some of the benefits of IMTA, how that you can have this circularization of the economy, which reduces waste and increases the production. What I'm going to go on to talk about a little bit in the next section is what are some of the bottlenecks. This really sounds like a good idea. Why hasn't industry taken it up already? How can we help industry to develop IMTA and this sustainable form of aquaculture further?